Welcome to Web Handling. My name is Dave Roysam. I am super excited to continue our new mini-series on measurements. In this short clip, we discuss another most serious mistake in problem solving using measurements. That is, data mining. That is, going on a fishing expedition in hopes of finding some correlation to waste, delay, or customer complaint. I know your time is precious, so let's get started. In previous clips in this series, we discussed in detail the targeted working theory of the objective function. That is to say, for example, that O might be a function of X, Y, and possibly Z. DOEs, a formal testing method, can be used to test the strength of any possible correlations. What we did in last week's show is showed many ways to improve the selection and measurement of the objective function itself, so that your trials can be quicker and your results surer. Okay, so much for a review. What we are going to do in this clip is to warn about the dangers of going on fishing expeditions. Whether or not your sensors are correlated and trustworthy, and whether or not the trials are constructed with the best practices for DOEs, and whether or not the results are statistically strong. There are many risks to contaminate the data with hope, or in more concrete terms, bias. We all want to be successful in finding a solution to our expensive waste, delay, or customer complaint problem. Yet, if we try too hard, we will find something, and that something may be misleading or even dead wrong. Of course, we all know that correlation does not imply or does not equal causation. That is why statistics, no matter how strongly performed, cannot be totally satisfactory in themselves. To be totally satisfied, we also need perhaps science, such as the collected science of web handling that I and others have taught for 4 decades. For those of you who enjoy poking fun of statistics, there is an abundance of examples to be found on the internet. Take, for example, just this one of 10 graphs found on just one site alone that clearly demonstrates that correlation, no matter how statistically significant, isn't necessarily causation. Here we have an exceedingly high correlation between divorce rates in the state of Maine and the per capita consumption of margarine, a butter substitute, in the U.S. This decade of data, which each point on the graph representing thousands or even millions of individual cases, seems at first sight compelling. The statistics can be checked by using Pearson's product moment, Spearman's rank, Kendall's tau rank, or Goodman's gamma, or the z-test, or whatever other test you wish, and find this correlation to be far better than anything you will ever find in your own plant. Yet, there's not a cause and effect connection whatsoever between these two variables. Those of you who have studied formal logic, such as the module that I teach in my advanced 2-day industrial problem-solving class, will recognize the statistical fallacy going by the Latin phrase of post hoc ergo propter hoc, or post hoc fallacy for short. In everyday language, this is simply that correlation does not imply causation. There are 5 possible relationships between variables A and B, only one of which, the first on the list, is causal. The second on the list, B causes A, is often given the common saying that a rooster's crow does not bring the sunrise. Worse yet, connections in the real world are seldom as strong as taught in logic. That means that statistics are even less trustworthy as evidence of connection because they are subject to the same fallacies listed here, plus the additional weaknesses of sensor and process variability and many other factors. P-hacking is a very commonly committed statistical sin. It is almost guaranteed that you will transgress this if you have enough measurements or sensors. Recall from our previous show in this series that some paper mill complexes record data from 10,000 sensors. However, you can sin using far fewer sources, say 100 or perhaps as little as 10. The sin is only reporting those data pairs that have statistical correlation. I have been in 100 meetings where some black belt committed this sin in front of a dozen of their bosses, peers, and minions, and no one challenged it. Even though I'm pretty sure that some in the room were not persuaded by the statistical correlation. Oddly, this statistical sin is not prevented by statistical analysis. It is, however, prevented by good experimental design with special attention to certain setup details. So, how do we avoid the quite common Six Sigma sin of p-hacking? Well, some of this has to do with good experimental design, perhaps beyond what is taught in your more basic DOE programs. The first and most important remedy is to make your hypothesis first, before you design the experiment, and certainly long before you analyze the results. In other words, we are intentionally selected in an inductive rather than deductive analysis. This working theory is most desirably constructed by well-established science or long experience if the science doesn't exist in the literature. I practice these principles regularly and quite simply when I do tests in the field. Together, after reviewing everything we have observed, the process engineer and I make a hypothesis and design a quick test, usually just 2 wound rows, where a single parameter is slammed from red line low to red line high. Then, just before this test is started, I predict the results based on the collective sciences and experiences. However, when measuring the results, I remain blinded by intentionally not knowing which role is which. Then both the blinded me and the unblinded process engineer, as well as an experienced operator, all look and compare the 2 wound roles. The experienced operator is often essential here because they are more experienced at looking at the roles and are usually less biased towards any particular working theory. They just want things to work without hassle, no matter whose theory it is. There are several other best practices of experimental design in general and how to avoid p-hacking in particular, and I will leave that up to the reader for their own homework. There are 3 starting points for a more detailed discussion of problem solving using measurements. The first is my industrial problem solving book that is a good companion to my industrial problem solving course of the same name. The second is the must-have 750-page Web Handling Handbook, written by myself, Tim Walker, and Dylan Jones. This is where we would look for the targeted and objective measurements for most web and role defects that are science-based, which can help avoid going on unnecessary and fruitless fishing expeditions. Last but not least is my award-winning and trademark Web 101 class that has been taken by about 5,000 students just like you. Here, you will learn about web handling, winding, common converting operations like slitting, as well as a good sprinkling of problem-solving techniques. Thank you so very much for joining me in this Measurement Miasma mini-series. Please join me in the next clip where we will talk about how many measurements do you need to make a trustworthy conclusion. I think you will be quite surprised at how few or how many measurements this might be. If you have a topic you would like to hear about, let me know in the comment section below. If you found anything interesting or useful here, please like and share and subscribe. See you next time.